Thanks to Nicolas and Jean-François, of course, for making this event happen. It's a pleasure to talk here. I'm also happy that Baptiste yesterday gave a nice introduction to the theme of this talk. I think his main takeaway message was that hyperbolic geometry, hyperbolic surfaces, are not too dissimilar from maps. Also, random hyperbolic surfaces show many properties that are very similar to random planar maps or random maps on higher genus surfaces. So I want to continue a bit in this theme. I won't be discussing the high genus regime, but primarily surfaces of genus 0 with many boundaries, and the particular case of boundaries of length 0, which correspond to cusps. And in particular, I'll discuss some scaling limit results here that kind of strengthen the connection with maps, showing that in a certain sense, they're living in the same universality class. But before I'm going to enter into the probability theory, I want to kind of make the connection between hyperbolic surfaces and maps, the enumeration or the measuring of how many maps there are, more precise. So let me give kind of a general introduction to the story and kind of emphasize where there is a very precise relation between the two before focusing on the actual geometry of these surfaces. So let me give a bit of a recap of what Baptiste has told us yesterday. So we're dealing with hyperbolic surfaces. So these are surfaces with a constant negative curvature. So that means that every simply connected patch on this surface is isometric to some patch in the hyperbolic plane. So here represented as the upper half space with the standard Poincare metric on it. Now, if you recall, in this upper half plane model of the hyperbolic plane, the geodesics, they correspond to half circles on the x-axis or vertical lines there. So we also have geodesics on the hyperbolic surfaces that correspond to those on the hyperbolic plane, corresponding to kind of shortest paths within some homotopy class of paths. So if we're studying kind of general hyperbolic surfaces, we want to know something about kind of the full space of hyperbolic metrics that one can put on a particular surface, say a fixed topology. So let's fix some genus G, a number of boundaries n, and look at the set of hyperbolic metrics on such a surface with the requirement that the n boundaries are actually geodesic, so they're really of the type of the geodesics in the upper half plane. And we put in some boundary conditions, namely a sequence of positive or non-negative real numbers that specify the lengths of these boundaries. So let's call this space the moduli space of hyperbolic surfaces with prescribed boundary lengths. And these are viewed up to isometries. Now the space carries a natural Well-Petersen measure that we've already countered yesterday. And according to Wolpert's magic formula, it can be expressed very conveniently in terms of a set of local coordinates that are associated to pair of Pans decompositions of these surfaces. So in a pair of Pans decomposition, you select the maximal number of disjoint closed geodesics, you measure their lengths, L1, L2 in this case, and you specify some twist parameter along these closed geodesics that tell me how to glue the pairs of Pans along their boundaries in order to obtain the surface that you're looking at. Now, if you're being precise, you say these are not really proper local coordinates because moduli space, it has singularities in it. We'll only be dealing with volumes of these spaces or randomly sampled points in these spaces, so we can really forget about the codimension subsets of these moduli spaces corresponding to these singularities. So we're only really interested in hyperbolic surfaces that are generic, where such coincidences do not happen. So then these are certainly good local coordinates, and we have this well-defined measure on the space that is really independent of the choice of Pan's decomposition that one uses. And if I then measure the full volume of this moduli space, it is finite, and it defines the Wall-Petersen volume. And it's a famous result by Mirzakhani in 2005 that these volumes satisfy topological recursion, and in particular, as a consequence, they are all polynomials in the prescribed boundary lengths, or actually the squares of these boundary lengths. And the degrees of these polynomials, they increase with kind of the complexity of the topology that you're looking at. Okay, so this is the realm of hyperbolic surfaces. So let me draw a connection to maps. Now we think usually of the enumeration of maps as just counting how many maps there are with certain prescriptions. If we want to draw the connection precisely with hyperbolic surfaces, it is actually more useful to look at metric maps. So what are metric maps? They're just maps together with an assignment of a length to each edge of the map. So let me introduce in particular the family of cubic metric maps. So these are maps that only have vertices of degree 3, and then I assign to every edge a real length x of e, which has to be positive. So here's an example of a planar cubic map, and here is one on the torus, together with some assignments of lengths. Now we can then naturally look at some moduli space of these maps, very similar to the one of the hyperbolic surfaces, where I fix the genus of my surface on which the map is living. I fix the number n of faces of this map that I label from 1 up to n, and I fix the circumferences of these faces. So what is the circumference of a face? It's just summing the lengths of the adjacent edges. And this space of metric maps, it also comes with a natural measure, which is simply the Lebesgue measure on the lengths on the edges, subject to the restrictions coming from the circumferences. Now it goes back to Kontsevich proof of Witten's conjecture that the volume of these spaces, the Euclidean volume, is again a polynomial in these lengths L of the same degree as the Wall-Petersen volumes. The difference is that these are homogeneous polynomials, and they're related to the Wall-Petersen volumes in a very simple way by really just taking the homogeneous part of this polynomial of top degree. And you can give a geometric interpretation of why these two are related to each other, something that Baptiste also mentioned, that if I look at a hyperbolic surface with prescribed boundary lengths and I make these lengths very large, since the area of the surface has to stay constant by Gauss-Bonnet, I get this very thin surface, which essentially is like a ribbon graph, and we're used to thinking of ribbon graphs as being the same objects as maps on surfaces. So if I prescribe the boundary lengths of these four holes there, that's really the same as describing the circumferences of the faces of this map. So in the limit where all these boundary lengths tend to infinity, we're really only seeing the Euclidean volume of these metric maps. But how about finite boundary lengths? Because that's really where the hyperbolic geometry is living. I mean, calling this a hyperbolic geometry is a bit cheating. And in order to specify how the relation actually works, it is more useful to think of the generating functions of these volumes. And these are the natural analogs of generating functions of maps that we encounter in the map literature all the time. So in the case of maps, you would say, let me introduce a generating function of genus G maps with a sequence of generating variables that really count the number of faces of the degree equal to the index of this variable. So for instance, a map like this would contribute a weight that is Q5, because this is a face of degree 5, times Q16, because this is a weight face of degree 16, etc. So the generating function would be a sum over maps. You have to take out some symmetry factor, but really the contribution is a product of this weight Q depending on the degree of the face. So what is the natural analog for metric maps? Now, the degree of a face is rather the circumference of a face. So it's not an integer, it's a real number. So if you want to assign some weight to it, you would take a function of the circumference. So instead of a generating function, we have a generating functional, which depends, say, on some measure Q, on the positive real numbers. And then the generating function of, say, metric maps will be summing over all number of faces that one can have, and then taking a product over all circumferences of those faces as the weight that contributes to this generating functional. Now you may think, okay, what properties should this measure satisfy? Fact is, we know that for a fixed number of faces, the volume is really just a polynomial in L, so anything that integrates a polynomial is fine here. I'm not going to specify this any further. And indeed, this generating functional, you can actually obtain it from the generating functional of maps by taking some limit, where, say, the number of edges in your map tends to infinity. You chop away all the trees on these surfaces, and you get something that looks like a metric map. Now, an interesting fact is that this generating function, it depends on your measure Q only through something which is called the times. And the times are just the even moments of these measures. So where does this terminology come from? Well, this generating function in terms of the times is nothing but the generating function of certain intersection numbers that feature in Witten's conjecture, which was saying that if I sum over all genus and take the exponential, that you get a solution to the KdV equations. So how about Weil-Petersen volumes? So it's known by kind of relations on the level of intersection numbers that they can also be expressed in terms of these intersection numbers, and that they're related to the generating function of metric maps. And what is the relation? So now I'm including all hyperbolic surfaces with all possible boundary lengths, but with a weight for each of the boundary lengths, I sum over them. So that's the direct analog of the generating function for metric maps. And it's given by the same generating function with the times, but with some shifts in there. So these functions, for any genus, you can make them very explicit. There are very explicit formulas for them. So that means that also Weil-Petersen volumes, there are very explicit expressions that one can get for these generating functions. But one can really ask the question, what is the interpretation of this relation at the geometric side of things? Let me phrase this as an open problem. Is there a bijective, or at least a geometric interpretation between the relation between the generating functions on both sides? Even without having a bijective relation, one can ask the question, well, are at least these different families of objects in some sense in the same universality class. We already know that in the large genus regime, by Baptiste results, that it seemed to be the case. On this talk, I will focus on the low genus regime. And to talk the level of bridges, this is also a recurring theme here. We're looking for bridges between theory of maps and the theory of hyperbolic surfaces, not just because we like bridges, but we like to use bridges. And I think this is quite a useful thing to do, because the type of techniques that people use to study geometry on hyperbolic surfaces is kind of complementary to what we're used to doing on maps. Just to give an example, hyperbolic surface people, they like loops, hula hooping, while map people like trees. So can we get hyperbolic people to like trees, and can we like, make the planar map people to like loops? Let's see. Oops. So I'll focus not on the general story of any genus. I will focus here just on genus 0 and the particular case where all boundaries are actually of 0 length. And let's see how we can take the trees across the bridge. Right, so from now on, the moduli space of genus G and n boundaries will mean the ones that have 0 boundary length. So now we have cusps instead of geodesic boundaries. So just to set the stage, why do we like trees? Well, we've seen yesterday already in these 2 occasions, in Jeremy's talk and also in Mathieu's talk, that trees play a very important role not only in enumerating maps, but also in studying their geometry. I'm not going to give a definition of a planar map nor a quadrangulation. Let me just flash that one could associate to any quadrangulation a labeled tree by labeling all the vertices of the quadrangulation by the distance to some marked vertex, and then applying this menu to it, which draws a tree for my quadrangulation. And if I then have the labels, so the distances on this tree, perhaps shifted to be 0 on the root, then you can fully reconstruct the quadrangulation by going around the contour in the way that we've seen yesterday. Right, and these labels, they encode distances, so they really tell you something very precise about the geometry of these maps. So where are these trees in the case of hyperbolic surfaces? So one thing one should notice here is that in some sense the tree one is drawing on this quadrangulation, it is like the complement of all geodesics that are running towards your marked vertex in a particular sense. So if you would look at all the leftmost geodesics that run from the vertex towards the marked point, and you would distinguish all these edges, then there is kind of a way in which you can find your distinguished tree as running around, or okay, I'm not going to make this precise, in which it's the complement of the union of all geodesics that run here. Let's keep this mental picture in mind, because this is the natural way to look at the hyperbolic surfaces. So suppose I have a hyperbolic surface with any number of punctures, where I have 2 of them distinguished, and I'll always kind of label one of these punctures or cusps. I'll use punctures and cusp interchangeably. I'll label it by a star, and this is going to be the origin of our surface, so the analog of the marked vertex in the quadrangulation. So what I want to do is I want to look in the surface to all the geodesics, the shortest geodesics that run into this origin. So I do kind of a breadth-first exploration of my surface. Now, since these are cusps, these are infinitely long, all these geodesics actually have infinite length, but still we can make sense of which ones are shorter than other ones. For instance, if I have a look at this circle here, this is a horocycle, and it's a well-defined notion of all points that are at equal distance from this infinitely far away cusp. So I can explore my surface further, and at some point I'll reach regions in my surface where there are more than one shortest geodesic into this cusp. And I'll also find points where there are 3 shortest geodesics into the cusp. But generically, there will not be points where there are more than 3 of these. So if I look at the cut locus, or if you like the spine, of this single origin cusp, you can show that it corresponds to a tree that is built out of geodesic segments that either start and end on a cubic vertex, or they end on one of the cusps. So generically, except for very special points in this moduli space, I will get a plain binary tree which has a number of leaves exactly equal to the number of cusps minus 1. So this one is not in there. And we'll see in a minute that you can look at the angles at where the edges of the tree meet, and the angles, they satisfy a relation, namely that if I add up the angles opposing an internal edge of the tree, that they're always larger than pi. So the main bijective theorem here is that there exists an open subset of the moduli space that has full Weil-Petersen measure, such that this is really a bijection with the family of all plain binary trees that are rooted at the other distinguished cusp, together with assignments of angles to the vertices. And the only constraints that these angles have to satisfy is that all the angles are between 0 and pi. So if I only specify 2 of the angles, I have to make sure that the third one is also smaller than pi, so that's the first relation. And then the second relation is that whenever I have an internal edge of the tree, the opposing angles have to add up to larger than pi. So this is the bijective part, but of course we want to kind of count these surfaces using the measures that we have. And you can show that the Weil-Petersen measure under its bijection is really mapped to the Lebesgue measure on the angles. So let's give some elements in the proof of this bijection. And the idea is to take your cut locus and consider a dual triangulation of the surface. So what does that mean? I know that all the points that are living on the edge of the cut locus have exactly 2 shortest geodesics. So let me take any point on this edge, concatenate the 2 shortest geodesics into the origin, so that gives a curve that starts at the origin and ends at the origin. And we know that within the homotopy class of such curves, there is always one that has shortest length. So there is a unique dual geodesic that leaves the origin and returns to it in the topological class of curves that cross this edge. So if I associate to all of the edges of my cut locus the dual geodesic, you can see that for every internal vertex of the tree, I'll get a triangle, which has all its vertices at the origin. And this is a hyperbolic triangle, meaning that it has 0 angles, an ideal hyperbolic triangle. It has 0 angles. And it extends to a full triangulation of the surface if we kind of include not only the geodesics that start and end at the origin, but also the shortest geodesics from the cusps to the origin. So we have a collection of ideal triangles, and in order to retrieve my surface, I have to glue these ideal triangles together again. And since every ideal triangle has the same geometry, the only freedom you have in gluing them is specifying how two sides of an ideal triangle are glued together. Now, since these sides have infinite length, there is a real degree of freedom there that shifts two triangles with respect to each other. But if I keep track of where the cut locus is within each of the triangles, well, then it's clear how to glue them, because I just have to match up the two ends of the red edges here. So the question becomes, within each triangle, how can I specify the position of a red vertex? If I know the position of a red vertex, I know how the edges will run, because they have to be perpendicular to the shortest geodesics. So let's see how this works in the upper half plane. So I take one of these triangles. I can always put it in the upper half plane with vertices at 0, 1, and infinity. And I want to ask, well, where can I put the center vertex for my triangle? Well, in principle, I can put it anywhere in the upper half plane, because I can always find, starting at the vertex, a geodesic. So remember, that was a half circle on the x-axis, perpendicular to one of the sides of the triangles. And I claim that the position of the center of the triangle is specified exactly by the angles that are made by the three edges that meet there. And this is kind of easy to understand if you believe that if I draw the straight line segments that connect this center to 0 and 1, that you can just read those same angles at the intersection with the x-axis. Then it's clear that wherever I put my point in the surface, it need not be inside the triangle, it can also be outside the triangle. That is uniquely specified by these angles alpha 1 and beta 1, because if I just draw these two half rays, they will intersect in a unique point. But of course only when alpha and beta add up to more than pi, otherwise these two lines do not intersect. So there's a bijection between this set of angles within a single triangle and positions of a vertex in the upper half plane. So if I want to retrieve my full surface, I need to glue triangles together, pair by pair. So let's look at a neighboring triangle. It will also have a center, say this one. But now there can be an issue, because the centers need not be inside of the triangles. So if they're allowed to be outside of the triangle, we can get collisions between the centers. So if we want them to be able to match up into a tree that is eventually living on this hyperbolic surface, I have to make sure that the center of the left triangle is to the left of the center of the right triangle. So what does that mean for the angles at the intersection? Well, using the construction here, this angle I can read it here, this angle I can read it on that side. So making sure that this one is to the left of that one is just making sure that these two angles add up to something larger than pi. So these two conditions were exactly the two conditions that I was imposing in the angle assignment to the trees. And if they're satisfied, I can consistently re-glue all these ideal triangles into my hyperbolic surface, and this is really a bijective correspondence. Now, just like in the case of the Curie-Vauquelin-Schaeffer bijection, these trees should somehow encode something about distances in this map, or map in this case in the surface. So somehow the angles should say something about distances to the origin, and indeed you can show that if you know alpha and beta here, that you know the differences in the distances of the three sides of the triangle, which are the distances between the three edges that meet at the vertex to the origin. And they're related through a hyperbolic sine law. And this also helps to figure out what is the measure in terms of these angles, because we saw Wolpert's formula for the Weil-Petersen measure, but Penner gave another formula in terms of a different set of coordinates, which were exactly all the lengths of the sides of an ideal triangulation of a surface. I gave an explicit formula. If we plug in this hyperbolic sine law with some algebra, we get exactly the unit Jacobian, and so a Lebesgue measure for this volume. So these are the ingredients in the proof. Okay, so let's see an application of this bijection. As we said, it encodes something about distances. So it allows also to say something about the statistics of the geometry when I take the number of cusps to be very large. So let's look at the random surface. So we had this finite, this Weil-Petersen measure with finite total volume. So we can normalize it into a probability measure. Let me call that Sn. And it defines for us a metric space if we equip this set with the hyperbolic distance of the hyperbolic surface. Now, one kind of technical difficulty is that this metric space is not compact, exactly because of these infinite cusps, which is an artifact of working with the zero boundary length hyperbolic surfaces. So if we want to talk about scaling limits, it's always much easier to work with compact metric spaces. So there are several ways to actually turn this into a compact metric space. One thing one can do is find a horocycle around each of these punctures. So the circles around a puncture that are a constant distance from the puncture. And one can choose them canonically by specifying the lengths of those horocycles. For instance, I can ask them all to be of length 1. If I choose length 1, then I also know that they all will be disjoint from each other. So it's a sensible operation to do. And then I can look at the metric space, which is just the finite set given by the horocycles and the distances between those horocycles. Now, if I normalize these distances by the number of horocycles to the -1/4, then what we show is that this converges to the Brownian sphere. So kind of corroborating this idea that hyperbolic surfaces live in the same universality class as random planar maps. One can also kind of apply the scaling limit to slightly different metric spaces. One can, for instance, consider the hyperbolic surface by which I chop off all the interiors of the horocycles. Then, if I know that every point in my surface is really close to a horocycle, and in fact, this distance is always a lot smaller than n to the 1/4, then actually the scaling limit also applies to this compact surface. If you really want to talk about the full surface, you really should not be working in a Gromov-Hausdorff topology, but you can, for instance, look at a Gromov-Prokhorov topology of metric measure spaces. So I equip the hyperbolic surface with the area measure normalized to have total measure 1. And then we have convergence to the Brownian sphere with its natural normalized measure. So there is this explicit constant appearing in front of the Brownian sphere. So yes? Yes. Why? So this is a nice theorem in hyperbolic geometry. So essentially, if you bring two, so how could it not exist? Let's ask this. You would say, well, if these cusps become very close together, they may, the horocycles may start overlapping. But this does not happen because you always have like a color around any either a cusp or a closed geodesics where nothing is happening. So if you make the lengths of your horocycles small enough, you know that they exist and do not intersect any other closed geodesics or horocycles of the same length. So this is actually really pleasant about working with hyperbolic geometry compared to, say, maps or general Riemannian metrics on the surface, that things never touch each other. Let's put it this way. But okay, let's also mention that.
What is the notion of length of a horocycle?
Well, this is no, a horocycle is just a circle embedded in your surface.
So but what you say is that sometimes the one you should have replaced by something else, by epsilon smaller.
No, I've not mentioned an epsilon.
No, because you said you said something about the fact that.
Okay, but if you try to bring two cusps close together, then automatically the cusp will also widen. So it will never happen that the horocycles will get close to each other when you do this. In some sense, the saddle you have in between two cusps, it will also move out to infinity or further to the right if you bring them closer together.
You would consider horocycles of length r, and there will be this phenomenon of. You mean that only r there are horocycles which do not overlap, or there is?
Yeah. So if you take horocycles length 10, then they can overlap. But there is an interface exactly somewhere at 2 or 1 or 1 point something where you're sure that they cannot overlap. And then whether I choose 1 or any other number smaller than 1, it actually does not affect the distances. It just adds a constant to every distance if I choose a different horocycle. So I just want to mention briefly where this constant comes from, because it's related to some of these connections between hyperbolic surfaces and maps that are still mysterious, but apparently some exact formulas exist. And this is a conjecture that I mentioned here that actually came out of looking at the topological recursion of hyperbolic surfaces. So what does it amount to? So it amounts to a generating function of, again, Peterson volumes on spheres with only cusps. But now I have 3 distinguished cusps. And I look at the difference between the distance of one to the origin compared to the other to the origin. So I weight the Peterson volumes by the exponential of some real number u times this difference. And then I sum overall number of cusps. So it seems like there is a very explicit and remarkably simple closed form for this generating function. So let me explain a bit how to interpret the right-hand side here. So R is really the generating function of Peterson volumes, now with just 2 marked cusps and any number of remaining cusps, which is well known to satisfy an equation in terms of Bessel functions, which you can also get exactly from this bijection between hyperbolic surfaces and trees by working out how these trees decompose into subtrees. So we have a formal power series in X here. So that means that if I plug it in this function, which has a branch cut, the coefficients of X will actually be Lorentz series in U. So what I mean by this notation is that we have to drop all negative powers in this Laurent series. And then we get here a formal power series both in x and u, and the claim is that it exactly gives you, the insight into the statistics of these differences in distances. In principle, one should be able to prove this theorem using the tree bijection, but the integrals that are involved in general, they're just, well, above my head at the moment. But the simplest case one can prove, so when order u squared, so if I just look at the u squared term, that's just including the distance squared, so that gives you insight into the expectation value of the squared distance difference in these surfaces. So in particular, it tells us, when I take the number of cusp to infinity, that the square of the distance grows like the square root of n, indeed showing that the typical scale of distances is of the order n to the 1/4. And the constant appearing in here is the first zero of the Bessel function. So I can compare this with the corresponding quantity of the Brownian sphere. When I take 3 different points there, then I know that it's given by square root of pi over 8. So that gives kind of a fairly simple expression for this overall scale of the hyperbolic surface in terms of the Bessel zero. But in principle, there is a much more general story here that is yet to be uncovered. Okay, several minutes remaining. Let me give some elements of the proof. And this is just living in the universe of other proofs of convergence to the Brownian sphere. We have a tree. Now we just have to find a way to fit this tree into the general framework. So let's mention the main technical result that we have to show. So I'm sampling a random surface. So that corresponds to first sampling a random binary tree proportional to the Lebesgue volume of the angles that I can associate to this tree, and then sampling random angles within the allowed angles for this tree. Then I said you can compute distances in your hyperbolic surface in terms of the angles using the hyperbolic sine law. So let me put those distances on the edges of my cut locus and shift them such that I have label 0 on the root. Then I know that the label on the edges that are incident to the leaves exactly correspond to distance differences of the corresponding cusp compared to the root cusp. And what we generally do with these trees is encode them in terms of certain processes, contour processes. So I simply have the combinatorial contour process that it runs around the contour in clockwise direction, visiting an edge at each step, and keeps track of the graph distance of the adjacent vertex to the origin, or sorry, to the root of the tree. I want to keep track of the label as I run around the contour of the tree. And for technical reasons, we also keep track of the number of leaves that we've encountered so far in this contour. And what we want to show is that this contour process normalized by square root of n, the labels normalized by the fourth root of n, and the number of leaves so far normalized by the total number of leaves scales towards a Brownian snake, so a Brownian excursion, E of t, a Brownian snake which encodes kind of the labels on top of the CRT that is encoded by the Brownian excursion. And the leaves that we count, it should just scale towards a linear function. Now I'm not going to specify the details here, But given that it's just after Christmas, you all have this experience that you go to the tree market with the kids, and the kids, they point at that tree, we need this one. And then you have to make sure to get it home. But often you encounter when you get to the parking lot that it doesn't actually fit in the car. So it's similar here. I was the kid, I had the tree. I went to Nicolas and he had the car, but Okay, so of course what you first have to do is you have to make the trees random size to have a chance of be able to describe them as Galton-Watson trees. So we make them their size random, we make them critical by choosing appropriate weights for the number of leaves. But the real problem here, and the reason why this tree will not fit in this car, is that the offspring distribution of the tree, it actually depends on the labels that are sitting on the vertices. So really these trees, they're like continuous type Galton-Watson trees. And the cars we have, they deal either with a single type or multi-type, but I'm not aware of continuous type tree invariance principles. So Nicolas told me that we should take trees that we can actually disassemble. This is the modern version of the Christmas tree. So the question is how to disassemble the tree to fit it in the car. And actually there's a really natural way of doing this on the level of the hyperbolic surface. So remember that for every edge in the tree, one could find a dual geodesic starting and ending at the origin. And sometimes this geodesic crosses the edge in the tree, but sometimes it does not. Right, so there are these. Right. Here we have a delay. Yes, right, so these are the two options. Now, conditional on the event that it does cross the edge in the tree, suspense, okay, we can actually separate the surface into two surfaces, which in the setting where the number of cusps is actually random, the two parts are conditionally independent of each other. So this smells like there should actually be a single type Galton-Watson tree hidden inside of this continuous type tree. And indeed, if I look at the triangulation associated to this tree, one can divide it into blobs exactly at these kinds of geodesics. And then the tree we want to be looking at is really the tree in which every black vertex corresponds to one of these blobs. So this really has the law of a Galton-Watson tree with an explicit offspring distribution, except that the root has a slightly different distribution, which is exactly the distribution necessary to make this random tree rerouting invariant, which you usually do not have for Galton-Watson trees. So to recover the original tree, what one first has to do is to reinsert the cusps of your surface, and they can be either 0 or 1 at each of the black vertices, and the probability depends on the degree within the black tree. As soon as you've done this, for every black vertex, you have to independently sample a couple of triangles that are glued to each other, so the blobs. So there is a probability measure on the angles on the red tree that is inside of this blobs that is slightly different from the probability distribution for the trees for the whole surface, but it's manageable. And then we need some estimates on these objects. And importantly, one needs to be able to deal with the distances in the surface at the level of the single type tree. So if I transfer kind of the random distance here, which depends on the interior of these blobs, two random labels on the black tree, then there is actually a very nice property here which sets this apart from many of the map bijections. And that is that these random labels are very symmetrical. In particular, they're locally centered. Why is that? Well, if I have a blob like here that determines the increment in the labels, then it has equal probability as the mirror image of this blob, which exactly has the negative of this increment. So all of the increments on this tree, they have zero expectation value and some good moments, putting them precisely in known invariance principles. Okay, so this gives the convergence to the Brownian snake, and then the most important, because there are some technical then challenges to transfer the convergence from the black trees to the original trees that I'll not comment on. An important additional ingredient in order to get the convergence of the full metric space is to be able to bound distances not just between cusps and the origin, but between arbitrary cusps. Now what we've seen is that we can produce this surface by gluing ideal triangles. So that is saying that we can find an ideal polygon in the hyperbolic plane such that kind of identifying the sides of the polygon I get the original surface. But you can do this in several different ways. And there is actually a more convenient way of writing this as a polygon in the hyperbolic plane that gives you access to the distances between two cusps, or at least upper bounds on them. And that is to cut open your surface not like here along geodesics that run to the origin, but along the tree itself. And along, say, one geodesic that goes to the origin. So then I'm putting my surface in the upper half plane with the origin up at infinity. The horocycle around the origin will correspond just to a horizontal line. And all geodesics to the origin correspond to vertical lines. And here I will have to make identifications on the bottom of this polygon in order to retrieve my surface. But in this particular polygon, I can easily find some geodesics between cusps. So for instance, if I'd like to find a geodesic between this one and that one, I just have to take a half circle that starts and ends there, which is not necessarily the shortest, but it is one geodesic. And in principle, one could compute exactly its length, but just to get an upper bound, it is sufficient to follow the curve that runs towards the root, the origin, then traverse horizontally and go back up again. And in order to upper bound the length of this curve, you certainly have to go above, so everywhere where the cut locus is. That is related to the minimum of the labels along this tree. Then if you go even a bit higher, it's useful because you can neglect the horizontal distance, meaning that we get an upper bound that really just depends on the vertical distances that we have transferred. So you get an upper bound between these cusps given in terms of the distances from the cusps to the origin and the minimal label in between. So this, together with rerouting invariance, gives, with the standard techniques, the convergence to the Brownian sphere. Okay? So I leave some perspectives up on the slides and open the floor for questions. Thanks.